All right, welcome back to Differential Equations. We're going to go through a few examples here. I'm going to break them up so there's about two videos, or two questions per video rather, so that way you don't have to plow through an hour-long video to find the problem that you're looking for. Okay. The first one is going to be a carbon dating problem, and the second one in this one is going to be a Newton's law of cooling problem. So here's the problem that we have. Archaeologists use pieces of burnt wood. Pieces of burnt wood. To date a prehistoric site. Right? We're given that the half-life of carbon-14 is 5,370 years. Half-life means that's when half of it is left. Just in case you haven't had a chemistry class yet. But so if I've got to start off with 100 grams of this stuff in 5,730 years, I will have half of it, 50 grams. Now, the other parts, the really interesting part of chemistry and physics, where you get to chase down what they call daughter isotopes, because this will expel either some kind of a photon, so it'll expel like a gamma particle, or maybe an electron, a beta particle, or I don't think it expels alpha particles, but because you lose like too much when you do that. But yeah, there's a whole field of study that deals with tracking how much of what this turns into after it expels particles, and there's often a chain. Okay, so that's just kind of a neat thing. They said that this sample had lost. Be careful when you're reading the problems here, because if you had college algebra at C&M, we would usually say it has so much remaining. This book decided that it's going to flip the script, and it said it has lost 86.5% of the carbon-14. Okay, and I have to remind my college algebra students and my pre-calc students that this 14 has absolutely nothing to do with the problem. Okay, we're not concerned about the kind of carbon it is. I mean, it's nice that we get to study things like carbon-14, but this 14 doesn't have an impact to what we're going to be doing. Okay, and the question is, how old is the site? Okay, so we're going to go through this. We can make the assumption, right, that radioactive decay follows an exponential model. Or in the language of our differential equations, that the amount of carbon is proportional, the rate of change, right, is proportional to the amount that we have. Okay, so the amount of the change in carbon is proportional to the amount we have. If you have more particles able to start expelling stuff, then that kind of makes sense. You have a lot of carbon, you have a lot of radioactivity going on. You have a little bit of radioactivity. Okay. So we're going to start with this. Okay, and we really have two givens. Even I know it only looks like we have one, but we're going to say that the half-life is 5,730 years. And our second given is that the amount of carbon we started with was the amount that it had when it died. So at time 0, Q was equal to the original amount. So that doesn't sound like a given, or that sounds too obvious. Like, yeah, but we need it. The fact that Q doesn't actually come up we don't really ever need this number, is fine. I always got really frustrated with some physics teachers who would give you a problem and then they would, like every time you worked the problem, you had a mass, and they didn't give you a mass. I mean, it drops out, but you go up to them and say, you forgot to give me a mass. They said, you don't need it. And now it was a harder problem. What I found is that you could cheat. You could say, well, my mass is equal to 10 kilograms. So in this case, we're not telling you what the original amount was, we're just saying an original amount exists, okay? But if it really bothers you not to have an original amount, then you could just say Q equals 100 milligrams, microgram, whatever unit you want to deal with, but just make it easy, say it's 100. You could say it's 1, okay? It doesn't, if I tell you that it doesn't matter what the quantity was, then you are free to pick whatever number you want. And if that makes the problem easier for you to solve, then so be it, okay? We're going to stick with just Q0 with our example. Okay, so we could go ahead, right? This is a separable equation. We could solve this, okay? So this is just dq over q is equal to k dt, right? We also note that q is greater than 0, right? Quantity is bigger than 0. So when we take our natural log here, technically we have absolute values, but since this is positive, we don't really need them. So this is equal to kt plus c. Now we're going to unlogify everything here. So we're going to get q is equal to e to the kt plus c, noting that e to the kt times e to the c, that's how the plus turns into a times in the exponent, and e to the c is a constant, so we're just going to say this is ce to the kt. Okay, so our equation here is ce to the kt. Right? Now we're going to note that at time 0, q was equal to the original amount. Okay, so we're going to say q is equal to, say q is equal to the original amount, so q naught is equal to c, and then e to the k times 0. This is just 1, isn't it, right? E to the 0 is just 1, so q0 was equal to c. So more, again, put a little refinement on here, q0 e to the kt. You could use whatever letter you'd like here, by the way. Okay, a for amount is fine, q for quantity. Okay, so there's our equation here. Now, we have another piece of information, is that the half-life, right, is 5,730 years. So, if t equals 5,730, how much stuff do I have? What's my q? Well, it's half the stuff I started with, okay? Equals q0 e to the k, and I have 5,730 here, don't I? And we're going to solve for k. And again, if you had college algebra or pre-calculus here, this should be a very familiar problem to you. Okay, so those cancel. Okay, so we have half equals e to the 5,730k. We're going to take natural logs of both sides, so natural log of a half is equal to natural log of e to the 5,730k. This bit will come down in front times the natural log of e, but we know the natural log of e is 1. We have natural log of a half. Now, when I learned how to do this, the trick they always pull on me, they say, well, natural log of a half is equal to the natural log of 2 to the negative 1, right? And then we can pull the same thing down and say, well, this is negative 1 times the natural log of 2. So you will often see that, and I'm just used to doing the problem this way, so that's, I think it keeps it a little bit cleaner when we don't have quite the fractions to deal with. K is equal to 1 over 5,730 times negative natural log 2. That's my K. for carbon 14. Excuse me if I just make this a K sub C or a K star or something like that so that we don't have to write down this number, because we're going to need scientific notation. It's like something times 10 to the negative fourth, but we're not going to write it down just yet. We're going to leave it in the alphabet soup, but we only have 3 letters, so it's not a very dense soup. Okay, we're pretty safe. Okay, so now we have our K. Okay. Now we can figure out, well, how old is this site here? Okay, how old is this site? Okay, now remember, it's lost. Oops, fix my pen here. Yeah, it is lost 86.5%. So 13.5% remains. Okay, be real careful. Like I said, the college algebra book tells you how much remains. This book is telling you how much is lost. So just be aware that don't go full autopilot and just assume it's going to be written the same way that the college algebra book wrote it, because it isn't. Okay, I'm sorry about that. So we're gonna solve for t here. Okay, so we're gonna say, well, we have 13.5% remaining. So we're gonna say we have 1, 3, 5 of the original, right? That's the percent, is equal to the original e to the kc, right? Times t. We're solving for t. First off, we could do is we could cancel our q zeros, right? We didn't need to know what these were anyway, so those are gone. We're going to take natural logs of both sides. We have the natural log of 0.135. I'm sure that's a delightful number. Is equal to the natural log of e to the k sub c times t. And this bit comes down in front, k sub c times t times the natural log of e, but we know the natural log of e is 1. It's equal to natural log of 0.135. And then t is equal to, right? T is equal to natural log of 0.135 divided by kc. And let's go over here. T is equal to natural log of 0.135 over natural log of 2, negative over 5730. Dealing with our fractions, we get this as t is equal to negative 5730 times the natural log 0.135, all divided by natural log of 2. Okay, we'll just run to the calculator real quick and plug this in. So we've got clear. So we've got negative 5730 times natural log. I know this is a decimal, so it's going to be negative number 0.135. And close the parentheses. It's very important to do that in this problem. Natural log of 2. And we're set. So this was about 16553 and some change. I think the original problem said rounded to the nearest hundredth. So 16600. That's how many years old. Okay, and there we have it. Okay, if all the problems were this easy, right, be a nice easy class. We're not going to be so lucky. Okay, so let's go ahead and turn the page on that one, and then we will talk about Newton's law of cooling. Okay, where are we? Okay, delightful. This was in the days, I remember doing all these problems in the early 2000s for students. The days when mother-in-law was still alive, we would watch NCIS 24/7. It's our favorite show. I would not say one disparaging word about NCIS or any of it. What was the other one she watched? Dead body. Was found. Hold on, I've got my local kitty here. Sorry about that. So where were we? We had a dead body was found in a closed room. Okay, of a house that was kept at a constant 65. That sounds so nice at this point. 65 degrees Fahrenheit. At the time. Okay. At the time of discovery, the temperature was 80 degrees Fahrenheit. Okay. 1 hour later, the temperature was 75 degrees Fahrenheit. CSI, that's the show I was thinking of, not CIS. CSI. Nobody shall disparage the CSI. Yeah. She had that thing about NCIS too, but watched a lot of CSI. Okay, let's see. So we're going to make some assumptions here, all right, to do this. So one, that the time of death, we have, this is what the problem in the book told us, the time of death corresponds to t equals 0. This problem is actually easier if you just allow time to be negative and say the time of discovery is time 0. So time of discovery equals t equals 0. That's actually a better way to go. I won't do it that way. I'll leave this one for you guys to sort out, but it is an easier way to go. Okay, so I would not write this condition on your quizzes, because I would let you kind of decide, do you want time of death to be 0? Do you want time of discovery to be 0? It's up to you. Okay. 2, that the time, or the temperature at time 0. So don't know how this person was killed or how they died, but the temperature at time 0, time of death, was 98.6 degrees Fahrenheit. Okay, so we're dealing with Fahrenheit here. And 3, they don't tell you this, but they either don't give you the equation and they don't tell you this, and I think that's wrong. So I would include, if I was writing this question, I would include that the change in temp, right, is proportional to the difference. It's a subtraction problem now, right? The difference, okay, in current temperature and environmental temperature. Okay, so I think this is an important piece of information to give you, because I don't want you memorizing Newton's law of cooling formulas. That's, you know, the fewer things you have to memorize, the better. Okay, so I would definitely say the change in temperature is proportional to the difference in the current temperature and the environmental temperature. Okay, and then the question is, when was the time of death? Okay. Actually, they give the corners, they give the people who investigate this stuff little cards so that they can do that. They don't have to do the arithmetic. The arithmetic's already been done. You've done this, and then you just tell them, like, if the temperature is this, you know, you have like a chart, right? An environmental temperature and current chart, and then it tells you like what time of death it is, and they just look on the chart. I also know that the FBI does extensive research on you know, putting dead bodies into various conditions and then seeing what the temperatures are going to be. So if you ever wanted to know, like, it wasn't in a variable it was a variable temperature. They locked it in the trunk of a car. How did that happen? That's what they do. Okay, so we're going to set this up. The change in temperature is proportional, constant of proportionality, to the difference of the current temperature and the temperature of the environment. Okay, so there's our starting point. Okay, so at this point, the calculus is not really all that tough, is it? This is equal to K dt. So we're going to be able to say something like natural log of T minus TE. I guess technically we should set this up as absolute values. Pretty much if we know this is true, then we don't need the absolute values. And if it's the other way, I mean, there was nothing that said that, it couldn't have been this way. It could have said the difference between the temperature of the environment and the temperature. So there's no reason why we would have to do this. So if you're dealing with, say, you've got an ice cold pop or something, ice cold soda, and you leave it on the kitchen counter, and the temperature has to rise to the environment, I would just switch them and do it this way and not worry about the absolute values at all. Okay, because there's no magical reason why this has to be like this. Okay, so if you're rising to an environmental temperature, that's one way. Or if you have found a dead body, like in a foundry or something at 120 degrees, we could do it the other way around. But this is KT plus C. Okay, but if this is true, if temperature is greater than the environment, then we don't need the absolute values. That's going to be true, right? 98.6 is a bigger number than 65, and it's not going to get lower than 65 because once the body gets to room temperature, right, it's not going to cool off anymore. Okay. So here we go. We have some algebra to do. Okay. Let's see here. What do we want to do? We want to say we have. We're going to unlogify this. Okay. Take the anti-log. So we're going to have T minus TE is equal to E to the KT plus C. So we have T minus T. So the E is equal to a constant, E to the KT. Okay. We have some initial things, like what happened at time of death? Time T equals 0, time of T. We had the temperature was equal to 98.6, didn't we? When T was equal to 0. Okay. So what we're going to have is 98.6 minus, what did they say, 65 degrees is equal to C e to the k times 0. So that's 1. Okay, so C is equal to the difference between these two, which, what is that going to give us? That's going to give us 32 or something, 33? 33.6. Yeah, I think we're okay there. Okay. So C is equal to 33.6. Hey, the difference between, right, the initial temperature and the environmental temperature. So solving for T, we're going to have T is equal to 65. That's our TE, right? That's our environmental temp. Okay, plus 33.6 E to the KT. Okay. Now we figured out our constant of integration, right? Now we got to figure out our constant of proportionality. This is why setting T equals 0 to be the time you found the body will be a lot easier, because if you don't, we just have to say, well, let T1 be time of discovery. And T1 plus 1 is equal to 1 hour after discovery, right? That is in hours. Okay, so we have two equations here, right? We have, what was the temperature at the time of discovery? Well, that was 80 degrees, right? So we have 80 is equal to 65 plus 33.6 e to the k times T1. Okay, and then an hour later, what happens? We have 75 is equal to 65 plus 33.6 e to the k, and then we have T1 plus 1. Okay, notice we have two equations, right? Two equations. We have two unknowns. We have T and K, T1 and K. We don't really care what T1 is. Okay, we're just solving We're just really solving for k. Okay, so when we have to do our substitution, realize that k is the important one. Okay. It's not a linear equation, at least not yet. So can't use linear algebra to help us. We're just kind of stuck dealing with two nonlinear equations, and yeah, I mean, there's 7 ways from Sunday to solve this thing. My way isn't the magic way, so if you come up with a slightly different way of doing this and it works, that's great. Okay, so this is not the magical way. So the first thing I'm going to do is I'm going to see if I can't isolate my k and my t, and that's going to be done by like getting exponential equations. So my 1 and 2, right? So equation 1 turns into 15 equals 33.6 e to the kt1. Equation 2 is equal to 10 is equal to 33.6 e to the kt1 plus 1. Okay. And then we could do something clever like, say, e to the kt1 is equal to 15 over 33.6, and e to the kt1 plus 1 is equal to 10 over 33.6. Okay, so let's see here. We're going to have a logarithm. So take the logs of both sides. We're going to have kt1 is equal to the natural log of 15 over 33.6. And we have kt1 plus 1 is equal to the natural log of 10 over 33.6. Okay. So here we're going to say something clever like k is equal to, we're going to say k? No, we're going to say t1 is equal to, so I'm going to substitute that one out. Keep our k's. So we're going to say t1 is equal to 1 over k times the natural log of 15 over 33.6. Okay, and then what we're going to do is we're going to take our equation 1 and we're going to plug it into equation 2. So we're going to have k 1 over k times the natural log of 15 over 33.6 plus 1 times the natural log of 10 over 33.6. Okay, so I took this equation here, right, and I substituted it into that one. Okay. So the k's here cancel. So we have natural log of 15 over 33.6 plus k, right? Plus k. And this is equal to, equals, parentheses, equals natural log of 10 over 33.6. Okay. So k is equal to natural log of 10 over 33.6 minus natural log of 15 over 33.6. I'm going to be just a little bit clever here, or I'm going to think it's a little clever. K is equal to the natural log of 10 minus natural log of 33.6 minus natural log of 15 minus natural log of 33.6. So this is natural log of 10 minus natural log of 33.6 minus natural log of 15 plus natural log of 33.6. Look at that, those cancel. So we get k, natural log of 10 minus natural log of 15, which is the natural log of 10/15, which is the natural log of 2/3. Delightful. Okay, now, right, we have, I'm going to go ahead and call that kt or k star. Okay, I think I put a little dot on it. Okay, so we'll do k star. Okay, is equal to this thing. Okay, just so we don't have to walk around with a big number like that. Okay, we are ready to go to solve the original time of death after all of that. Okay, pick whatever equation you'd like. I would prefer that you pick equation 1. Why? Because we only have a t, right? Like equation 1. So here we had it. What are we doing here? We have 15 is equal to 33.6 e to the k star t. We're solving for t now, right? Solve for t. This is 15, 33.6 is equal to e to the k star t. Taking natural logs of both sides. ln 15 over 33.6 is equal to k star t. And then what are we doing here? Saying t is equal to natural log of 15 over 33.6 divided by natural log of 2/3. Okay. And we plug all of that in. Right. Natural log 15 divided by 33.6 divided by natural log of 2/3. Okay. And we got t is about 1.98 hours. We're going to call that about 2 hours. Time of death, 2 hours before discovery. Now, if you had set t equals 0 for time of discovery and plugged it back in, you would get a t equals -2. Okay, so 2 hours before you discovered it would have been time of death, which is exactly what we found here. Okay, so time of discovery was 2 hours after this person died. Okay. All right, so I'm going to pause it. I'm going to cut it there. So that's our first one. I'm going to do a couple of mixture problems next, and then we'll see where we go from there. Okay, very good.